Well, actually, that was the idea that there are lots of conferences being cancelled and seminars also being cancelled, and we have a unique opportunity now due to this virus to talk together, and probably we can start some seminar and some forum to exchange ideas, and maybe in future we will have better organized situation so people can propose some seminars, we can discuss things and have a regular venue here. And today we will try the first one. Well, first one maybe is a difficult thing, and not everything works fine, but maybe next time we will do better. So let's not waste the time and begin the first seminar. And so Georgy Sharygin will give a talk today.
Excuse me, can I just interrupt for 1 second? Because I just noticed that in the invitation email, it says 4 time Moscow time and in brackets 2 p.m. UK time. So it's we have 3 hour difference with the game. Maybe you can just
2
reply.
hours difference now, 2 hours difference.
Okay, right, sorry. Yeah. Sure. Yeah.
Okay, we begin the seminar and we go to the talk. Georgy, yeah, we are waiting for you.
Okay. Okay, do you hear me now? Yes. Okay, great. So when I first talked about this conference with Dima Talalayev, he asked me to be very, very, slow in speaking about cross ratios and everything, so that so that young participants, students, could follow at least some part of my lecture. So I'll try to follow this design, and so if you find this to be too slow, please forgive me. If it's okay, then let me begin. So my talk will be about the very famous generalization, a very famous projective invariant called the cross ratio. So I begin with the recollection of some properties of this cross ratio, and begin with the definition. Suppose we have 3 points on a straight line. Let I call it A, B, and C. Then we can define the usual ratio, lambda of A, B, C, putting it to be equal to the, say, the ratio of BC, vector BC, and vector AC. Well, when I say vector, it means that it is equivalent to the identity that BC is equal to lambda times AC. In particular, lambda can be less than 0. In this case, in the case I have in my picture, both are, well, directed in the same direction, both point in the same direction. So this lambda is greater than 0. This ratio is definitely preserved by affine transformations of the plane and of the straight line. That's clear, yeah, because straight line preserves affine transformations preserve the ratio of collinear vectors. But unfortunately, if we try to do some kind of projective transformation, this ratio ceases to be invariant. And when I speak about projective transformation, I mean the following thing. Suppose we have this kind of picture. I enjoy drawing pictures and I enjoy elementary geometry. So with your permission, I'll draw a few pictures. This and something like this, say. I have 4 points. We have 3 points here, A, B, and C. And then projective transformation, we can say that projective transformation is given by looking from this point O at this straight line ABC and seeing that it is the same as a straight line A1, B1, C1. And it is clear that this relation, this ratio, is not preserved by, if you go from ABC to A1, B1, C1. ABC. There is chat going on here. If you want me to answer, feel free to ask the question. Next, so in order to make this invariant, people found the following generalization. They added the fourth point D to this picture. And then they introduced a cross ratio of 4 points by putting kappa of A, B, C, D to be equal to lambda of A, B, D, D, divided by lambda of A, B, C. Now this expression turns out to be invariant with respect to the change of from A, B, C, D to A1, B1, C1, D1. And if you allow me, I'll try to give a sketch of the proof. I like elementary geometry, I'm telling you. And I think it will be good for students to see that elementary geometry, in fact, is, well, is worth studying. Sorry, what's this? What's this? Something is wrong with my, sorry. So I begin with observing that the triangles ABC, AOC and BOC have the same height. If you draw a height from O to the straight line ABC, it will be common for AOB and BOC for all the triangles. So we see that now the ratio BC over AC is equal to the ratio of the areas of B, BOC with ratio with AOC. And on the other hand, we can compute the area of a triangle using the famous formula, which says that area of triangle with sides A and B and the angle phi between them is equal to half of the AB sine of phi. So this gives us one half is cancelled out. So we have a O times sine of, BO times sine BOC divided by AO times sine of AOC. And similarly, when you take AD, BD divided by AD, you obtain the same, but now you have BO times sine BOD divided by AO divided by times sine of AOD. So when you compute this cross ratio, you'll see that the kappa will be equal to the ratio of sines, something like sine of AOC divided by sine of BOC times sine BOD divided by sine AOD. And now it means that it only depends on the straight lines OA, OB, OC, OD. In particular, it will be the same for the points A1 through C1 through D1. That's very nice. I see. I like elementary geometry. And go on. This, yes.
Gosha,
Yeah.
Andrew Hahn wrote that the low part of your screen is invisible.
Ah, I didn't know this. Try to. That's strange. It's the first time this happens, because before that I made several talks in independent university.
It's okay on my screen. I think it's a setup of Andy.
Probably.
For me, it's completely okay.
For me, it's okay.
Yeah, I'm sorry. I tried to not to write in the lowest part, but I just
no. That is, Andy should try to clean his.
Okay. Shall I go on? Okay. So this cross ratio has lots of properties. So let me try to list. I'm trying to list some of them here now. So properties of the cross ratio. We begin with first. We can actually take away the geometry from now on from our discussion for some time at least by introducing the coordinates. We can take, for instance, so to say, affine coordinates, so that A has coordinates ZA, B, ZB, and so on. Then the cross ratio will have will look like the following ratio of differences: ZA minus ZC times ZB minus ZD divided by ZB minus ZC times ZA minus ZD. That's one thing. Next, we also observe that since I explained that this cross ratio doesn't depend, well, it is invariant with respect to projective transformations of the plane of the straight line, we can do the following thing. So we can projectivize everything. Projectivize as follows. We just now consider this affine line as part of the projective line. Then every point will be given two homogeneous coordinates, say ZA and WA, ZB and WB, and so on, so that now kappa will look like in these projective coordinates as ZA times WC minus ZC WA, and so on. And so on. I'm not going to write it down completely to save some time, but I think it's not difficult to write it down. And clearly, now it's evident that this formula does not depend on the choice of representative of homogeneous coordinates. If you multiply Z and W, ZA and WA by the same scalar lambda, it will cancel out here and here. So this is well-defined projective, well-defined number. It doesn't depend on the choice of projective coordinates actually, but what is even more important is that now you can first you can take Z to be complex, Z and W to be complex. I wouldn't be able to draw a complex picture at the previous slide. But then the projective invariance will follow from the following observation. You take any matrix A in SL2C such that A is equal, say, to A, B, C, D, and then you send a ZW into AZ plus BW CZ plus DW. And then you can, by straightforward computation, check that this expression, if you deprojectivize your formulas, will be invariant under the action of such matrices. So you can do this, well, very straightforwardly by direct computations without any geometry now. That's the first property. And it is traditional to call this expression either this or this, the usual cross ratio of 4 points. Can put this, regard this as a definition. What else? Actually, the following statement, we shall prove it a little later, but I think it is worth to mention it right now. It is the second important property of this cross ratio, that actually the cross ratio is the only unique and the projective invariant of 4 tuples of points in projective line. Of 4 tuples of points. Namely, there exists a projective transformation, that is a transformation of this form, such that phi of A is equal to A1, and so on, phi of D is equal to D1, if and only if corresponding cross ratios coincide. We shall a little bit later prove, well, not prove, I'll probably just explain the method of proving that the same is true even in a non-commutative case. Let's go on. Here is a third property which we can regard as an independent way to introduce the cross ratios. Now, well, you can think it to be more or less geometric depending on your tastes. Here is another definition, if you want, of cross ratios. Suppose we have 4 vectors. So we used to have 4 points in projective plane, A, B, C, D. Now we consider 4 vectors, A, Z, A, W, A, B, Z, B, W, B, and so on in, well, C2, for instance, or R2. Then we want to define, of course, this, if you projectivize them, then these vectors will go into the points in A, B, C, D in projective plane, and you can actually define the cross ratio of 4 vectors as the cross ratio of 4 corresponding points. But it is probably worth doing this geometrically in terms of vectors themselves. To this end, we consider the system of linear equations C equal to, I prefer to do it like this, A alpha plus B beta, and D equal to gamma A plus delta B. Then you can solve the equations, corresponding equations, using the Cramer rule. In the usual way. And you see that, say, alpha is equal to the ratio of the following determinants, Z, C, W, B minus Z, B, WC divided by ZA WB minus ZB WA, and so on. And this gives us the following way to define cross ratios, just by putting the kappa of A, B. Probably you should better write, spell kappa in different way, a different script. This kappa, okay, small kappa, C, D, to be equal to the ratio of beta gamma divided by alpha delta. Well, an alternative way is to remember that we actually don't have vectors A, B. If we have just points in the projective line, we can actually multiply them by arbitrary coefficients. So we can actually, from the very start, think that C is equal to A plus B. And then we can say that D should be equal to kappa A times B, sorry, plus B. And this kappa is precisely this. This geometric way of reasoning is pretty nice. First, it is nice to restore the previous properties of the cross ratio in terms of this definition. And one of the properties is that, for instance, K of lambda A, lambda 1A, lambda 2B, and so on, lambda 4D is equal just to K of A, B, C, D. And that just means that this is actually invariant of points in projective line, not of vectors. Then the property of being invariant with respect to the projective transformations means that K, when you multiply every vector by the same matrix G, a invertible matrix, of course, C, D, it is equal to K of A, B, C, D. So you see this, this is the way to say that this is projective invariant in terms of vector space. Yeah. And one of the most remarkable properties of these cross ratios is the following, is the way it performs under the permutation of, so this is the fourth property, under the permutation of points. There are actually several formulas. If you just compute the size of the permutation group as 4, it has 24 elements, so that will be a very large list of relations. I'll just give you a few of them. For instance, kappa of A, B, D, C. So I just permute C and D and do nothing else, is equal to 1 over kappa of A, B, C, D. And the most difficult expression is that, for instance, kappa of A, D, AD, ADCB is equal to kappa of ABCD divided by kappa of A, B, C, D minus 1. It's one of the most difficult formulas in this respect. So altogether, it gives you a famous, can be reduced to 5-term relations of bilogarithms. It can be related to 5-term relations of bilogarithms and so on, but we shall not discuss this today, most probably.
D logarithm, good.
Oh, yeah, D logarithm, sorry, how do you say, D logarithm or di logarithm? I don't know, di logarithm. Let it be dial algorithm.
Better to ask the
I'm not specialist in this kind of.
language carriers.
Yes, yeah, nobody cares. Okay, great. So now it is time to introduce the non-commutative version of all this story. And that was actually the reason why I spoke in geometric terms at the previous slide, because this geometric term can be very straightforwardly generalized to non-commutative case. So we pass to non-commutative case. And here is the definition. We begin with 4 points. So we choose a division ring F, non-commutative. So the reason for that, sometimes it's called skew field also. But this is actually not necessary for us to assume that everything has inverses. It is enough to assume that whatever we want to have inverse should have inverse. But yeah, anyway. So suppose we have a division ring or anything like this. So that whenever we want something to be invertible, it should have invertible, it should be invertible. And we have 4 points X, Y, Z, T in the Cartesian square of F. You can regard this as a kind of analog of R2 or C2. Coordinates of X will be denoted by X1, X2, and so on. Consider the following system of equations. It is very analogous to the one we discussed before. T equal to X alpha times Y beta. So here it is important to write coefficients plus on the right. Alpha and beta are coefficients from the field, from the ring. And Z equal to X. Now we can actually, using the fact that we have division ring and assuming that everything is invertible as long as we want it to be invertible, write the coefficient here in terms as a product of alpha and some gamma. And the coefficient at Y, we shall write even more straightforwardly as product of beta as before, gamma, and some new coefficient kappa. And then this kappa, which depends on X, Y, and Z and T, is called the non-commutative cross ratio of 4 points in the in the Cartesian product of F. It has lots of properties, this non-commutative product. I'll try to prove or at least explain some of them. We begin with the most important property probably. If you take arbitrary lambda 1, lambda 2, lambda 3, and lambda 4, multiply our vectors by these coefficients on the right, we shall not obtain the same, unfortunately, but we shall obtain something very close to it, and which will turn into this as long as our skew field is usual commutative field. Namely, we shall have lambda 3 minus first here and lambda 3 on the right hand side. To see this, one can actually follow just the definition. If you multiply it here, then alpha twiddle will be equal to lambda 1 minus first alpha. Beta will be equal to lambda 2 minus first beta, right? Here we shall have alpha twiddle, gamma twiddle, and so on, which will show you that this formula actually holds. Now, the second property is a bit more interesting, is that Actually, K, when you multiply all of them by the same matrix G from GL2, sorry, GL2, F, GX, GY, GZ, and GT, then it will be the same. And this is not that easy to prove, unfortunately. At least I don't know of any reasonable way of proving this unless you use explicit expression. Sorry, not Y, Z, of course, here. So here we have Z. Unless we use the explicit expression. So I think it is time for us to unveil the explicit expression for the K for this kappa. For kappa.
Gosha, excuse me.
Yes.
There's the question from Misha. Is the right projective space is isomorphic to the left projective space?
Oh, a very good question. I don't know. I don't think it is, unless we work in some very nice, or very nice skew fields. In quaternionic case, it's definitely the same. You can, well, it's the same up to the conjugation, but I don't think it is the same in more general case. The problem is that the definition of skew field is actually, well, at least over real numbers, there is only one genuine skew field, and that is quaternion. So I'm not that good in other, I don't know that many examples of skew fields and reasonably defined projective spaces, you see. So probably it need not be the same, just from the general case, from the general standpoint. I don't see why it should be the same. Okay. Probably, I don't see if Volodya is here or not. Is he here? And just, he can probably, since this part of my talk is very closely related to what he did, he can probably give more information than I can, but yeah, let's postpone this to a better time. Okay. Okay, so the explicit expression for kappa. We begin with the so-called quasi-determinants. Of Gelfand and Redach. Here is the definition. For every 2 by 2 matrix A, which you can write down as A11, A12, A21, and A22, and every couple of indices, ij equal to 1, 2, 2, 1, and so on, we can define as a determinant with the corresponding index boxed. For instance, suppose we have ij equal to 1, 2. And this quasi-determinant A11, A12 boxed, A21, A22 is equal to A12 minus A11, A21 minus first A22. Here we assumed that A21 is non-zero, of course. This is the assumption which we always shall be making. And it is easy to actually to remember the rule for the order of elements here. You can imagine that Aij is a map from I into J. Then we have a map from I from 1 into 2 here, from 1 into 1 here. Here, A to 1 goes from 2 to 1, but its inverse goes from 1 to 2. And here we have from 2 to 2 again. So actually, this rule allows you to restore all the corresponding terms in a unique way, pretty straightforwardly. For instance, if you take box, for instance, here, A21, box A11, A12, A22, and you begin with A21, it goes from 2 to 1. And now you have to use the remaining part of your coefficients to draw another map from 2 to 1. So you should begin with A22. Yeah, the inverse should go in the middle. That's the most important rule. Then you have A12 inverse. And then you have A11. And that goes actually for arbitrary metrics. For any metrics, for any square matrix, A in with coefficients in F, and any couple of indices, say PQ, you can define the determinant, quasi-determinant of A with coefficients with indexed PQ. And this can be done under the assumption that the submatrix A PQ, which is given by deleting the pth row and qth column from the matrix A, is invertible. We also take the following notation. We use eta PQ to be the qth column of A and psi PQ to be the pth row of A, but with A PQ removed. And now we can define a PQ's quasi-determinant of A to be equal to A PQ minus psi PQ times A PQ minus first times eta PQ. This is, well, it turns out that what you have in the middle, that this coefficient, this matrix, can be expressed in terms of quasi-determinants again. Of quasi-determinants. So actually what we have here is a recursion, which allows you to compute any quasi-determinant of arbitrary PQ. However, it should be warned by the following fact. If F is commutative, then APQ, this quasi-determinant, is not equal to the determinant of the matrix. It will be equal to the ratio of the determinant of the matrix by the determinant of the submatrix APQ. So this actually reveals the relation of these coefficients, of these determinants, quasi-determinants, and coefficients of the inverse matrix, because as you see, this is just up to the sign, is just the inverse of the PQth or QPth coefficients of the inverse matrix. So in general, we have this. And now in terms of these quasi-determinants, we can write down the following expression for kappa. Kappa of x, y, z, t is equal to this quasi-determinant y1, z1, y2, z2 minus first times y1, y2, t 1 boxed T2. Now x1, x2, T1 boxed T2 minus first, and x1, x2, x2, T1, T2. And if you work a little bit, actually by straightforward computation now shows straightforward computation. At least I know it as ways. I can do this by straightforward computation.
There should be mistaken two last terms.
Sorry? Oh, sorry. The last one is correct. You're right. Slip of hand. It should be, here it should be y1. Sorry, you're right. This is y1, 1, 2. Thank you. Y1, y2. Yeah. Sorry. Yes, it's been slip of my hand, I think. Oh, actually, when I prepared, I made a slip in my notes. I should remember. I should change this. Oh, damn. I think it should be. Yes. Either this. I think this should be T. I'm sorry. I'm sorry for. This should be T still. T1, 2. And this should be Y. I'm sorry I made this mistake. Y1, Y2. I think this now is correct. Oh, please forgive me if this is.
That's strange. There is one.
Yeah, you're right. This is something.
Wrong.
I think this is, yeah, there's something is wrong. Let me see. If you want, if you wait for a while, I find the correct formula. I'm sorry, just when I was preparing, slip of hand, which changed everything. If you wait for a while, that's the advantage of working from home. I can do this now. Okay.
Probably Z1, Z2.
Probably. I don't remember. Should be here. Should be here.
Because Z1, Z2 should cancel like everything else.
It should be. Yeah, should. Yeah, right. Like everything. I just need to choose the correct order. You see, that's the problem. All the rest is clear. You're right. Yeah, the last should be Z1, Z2. Right. now that's it. I just now need to find my whiteboard. Right, the last one is Z1, Z2. Thanks. I need to change this. Z1, Z2. Thanks. Now a straightforward computation shows that when you multiply your vectors by right-hand side, from the right-hand side by the same matrix, you take y times, I think not from the right, but from the left, from the left-hand side by the same matrix, and a x and y and so on. Then what you have, these coefficients in the middle, there will appear certain coefficients which will cancel out. So we have something something like the a y say 2 minus first, and from here we shall have x a y 2. As you see, it will count, it will cancel. And similarly from here we shall have a x 2 minus first, and from here we shall have a x 2. So it will cancel out, and we shall have the identity I promised you to prove. So this is the only way I can prove the invariance of this cross ratio. Okay, let's go on a little bit. And which is even more important, we have the following property, which is totally equivalent to the property of cross ratio being the unique projective invariant, is that suppose we have 4 vectors x, y, z, t, and 4 other vectors x prime, y prime, z prime, and t prime, right? And the claim is that there exists transformation of the form x goes to g x times lambda 1, y goes to g y times lambda 2, and so on, such that x goes to x prime, y goes to y prime, and so on, if and only if there exists mu in f, in the invertible part of f, such that k of x, y, z, t is equal to mu k of x prime, t prime, y prime, z prime, t prime times mu minus first. Well, the proof is pretty well straightforward on one hand. We just observe that, and yeah, one assumption we need to make, the assumption which I think was almost evident, is that k of x, y, z, t is not equal to 0 or 1. So under this assumption, we see that a sketch of the proof. We see that under this assumption, we can choose the vectors z and t to be the new basis. And similarly, z prime and t prime to be new basis in f, and using the matrix which will change the coordinates such that z t goes to 0, 1, 1, 1, 0, 0, 1. And similarly for z prime, t prime. We see that the matrix x1, x2, z, y1, y2, z1, z2, t1, t2 will go under this transformation to a1, 2, 1, 1, a1, 2, a2, 1, a2, 2, and here identity 1, 0, 0, 1, and similarly for the primed. Now, since we assumed that the cross ratios were the same, we see that we can compute cross ratios for the new matrices, and they will be equal to just the expression. Let me write it down. K equal to a1, 2, a2, 2 minus first, a2, 1, a1, 1 minus first, and similarly for primed vectors. And finally, it only remains to look for the diagonal matrices such that conjugation of these two matrices by diagonal matrices of the matrices A1, 1, A1, 2, and so on. So conjugate by diagonal will be equal to the primed. And this can be done just by straightforward computation. And this proves the theorem. at least the if part. The only if part actually has been proved before. And final, probably more interesting property of this, is it 4 or 5, I don't remember, of this cross ratio, is that actually all the symmetric group action formulas are preserved modulo some modification, are modified in a suitable way. They are not wildly modified to something unpredictable. They are they turn into something pretty easy to follow. Actually, you can introduce the following expression. You say that, where is it? Sorry, I forgot the indices. I need to look it up in my just a moment. Take me some time. Strange. Strangely enough, I cannot find this.
What's happened? What's happened, Russia?
I'm looking for the expression for the Pluke coordinates. I used to write them down. Ah, here it is. It is just. We can introduce the so-called noncommutative Pluke coordinates. By, well, you have x, y, z, and t, and so on. We write them down as before. Then we introduce the Pluke coordinate, say q, x, y, z, to be the following ratio of cross ratios of quasi-determinants: z1, x1, z2, x2, minus first, z1, y1, z2, y2. Right, then in particular, actually one can express k of a, x, y, z, t as q, y, z, t, q, x, t, z, t, z. And now the permutation formulas look as follows. For instance, if we take k and change the order of y and x and remain in t and z simultaneously, it will not be the same as it used to be in case of classical noncommutative ratio. In classically, there should be just k, x, y, z, t. However, here we need to conjugate it by the quasi-noncommutative Pluke coordinate of this sort. Clearly, what we have on the opposite sides are opposite to each other, are inverse expressions, so it's just conjugation. And well, there are a few relations of this sort which involve conjugation. Some of them are still look classically. For instance, k of x, y, z, t is equal to k of y, x, z, t minus first. Well, in general, we shall always have this kind of conjugation on both sides. So you should not be very careless when you work with noncommutative cross ratios and Pluke coordinates. Okay, this is already enough to prove few interesting things about noncommutative cross ratios. For instance, I'm going to speak a little bit about the so-called Pentagram mirificum, which in classical case is already quite interesting statement. So I'm going about the pentagramma Oh, not pentagram. Why? Pentagram. Pentagram mirificum. This is an observation made by Gauss, which is related to the following configuration on the sphere. Suppose you have a sphere. As you know, polygons and spheres can have arbitrary, more or less, angles. In particular, we can draw a pentagon on the sphere such that all the angles of this pentagon will be right angles. For instance, here, we can assume this to be right, and so on. Right angle, and finally, right angle again. So we have a pentagram. Let alpha 1, alpha 2, alpha 3, alpha 4, and alpha 5, alpha I, let them be the lengths of the corresponding arcs, the sides of this pentagon. Length in the sense that I'm working on unit sphere. Otherwise, I need to work with the angular measure of this of these arcs, of course. And let y I be equal to the tangents of alpha I squared. Well, for Russian students, this is abbreviation for what is usually abbreviated to TG in Russian. Then the following is true. This is the formula which Gauss liked very much. yi times yi plus 1 is equal to 1 plus yi plus 3. I is equal to 1, 2, 3, 4, and 5 modulo 5. That is to say, we may use the circular order of these angles, and then we obtain this kind of relation. The proof given by Gauss is very easy, actually. Well, it's easy, but it is involved in some respect. One can use the Napier a rule that is a kind of an analog of sine and cosine rule for spherical rectangle triangle, kind of sine and cosine rules for rectangle triangles, some kind of Pythagoras rule as well, to find 5 points P1, P5 in a real line, such that yi is equal to the cross ratio of pi plus 1, pi plus 2, pi plus 3, and pi plus 4. Not just this, I think I should also put minus here, because actually the formula is a little bit different. It is something like pi plus 4 minus pi plus 1 times pi plus 3 pi plus 2 divided by pi plus 4 pi plus 4 pi plus 3 times pi plus 2 minus pi plus 1. So it's up to the sign, the cross ratio. I think it should be minus. Then just from this relation, or from the properties of cross ratio, you can see that this relation holds. So this relation star is just consequence of the cross ratio relations of cross ratio. And it is really remarkable thing, actually. Lots of things it involves. If you are interested, you can look it up in a very nice paper by Vadim Shechman, where he discusses not just the proof of this theory, but also some of the consequences, I think, of its relation to various interesting modern mathematical theories. But for us, we need to look for the analog of this relation in case of non-commutative cross ratio. And it turns out that something very similar can be found. Well, somehow the problem is that it will not look as pretty as this relation of Gauss, but probably if we just change the notation a little bit, we can fit it into this, but I didn't try to yet. I haven't tried to do this yet. So now suppose, so in order to see the non-commutative analog of this relation, you can do the following trick. You can take again 5 points in projective, non-commutative projective space, or just 5 vectors in, sorry, x1, x2, and so on, x5 in F cross F, 5 points. Then you introduce, probably should better write not X, but probably P, because I used to denote it by P. So let it be P. P1, P2, P5. Then we denote by K, I, J, K, L, just K of P1, Pi, Pj, Pk, and Pl. And in this notation, we introduce the numbers x1 equal to minus k, 1, 2, 3, 4, x2 equal to minus. But here is some discrepancy notation, which I don't like, but I don't know how to rule this out. You see that the order of this signs is a little bit violated. It's not what you should expect. It is not cyclic order. X3 is equal to minus K, 5, 4, 2, 1. X4 is equal to minus K, 3, 4, 2, 5. And X5 equal to minus K, 3, 1, 4, 5. Next, we define X bar, Xi bar to be equal minus K. Now here we have the change the order of the first two coefficients. So if Xi is equal to K P Q R S, and here we have Q P R S. Yeah, and with this notation, we have the following relation, which is also just a straightforward computation with definition of cross ratio. For instance, x1 q132 x3 q123 is equal to 1 plus x2, x4 q4 5, 2, 3, x2, q 5, 3, 2 equal to 1 plus x3, x3, q 5, 2, 4, x5, q 5, 4, 2 equal to 1 plus x4, and so on until you come to, for instance, the next one is x1 bar, q3, 4, 2, x4, q3, 2, 4 equal to 1 plus x5, x5, q3, 4, 1, x2 bar, q3, 1, 4 equal to 1 plus x1 bar, unless I made a mistake writing this down from the paper, and so on. Actually, using this, yeah.
Of q with 3 indices.
Yes, q with 3 indices is a Plucker coordinate. Is non-commutative Plucker coordinate. I gave this definition a couple of pages before. Here it is.
Thank you very much.
Welcome. So here is this kind of non-commutative pentagram relation. And it's really interesting if the magic properties of the usual pentagram relation survive in this non-commutative case. So I just wonder how much time do I still have?
So it depends.
Well, I think 40 minutes. I think 40 minutes would be more than enough for me. Okay.
Just short question. What is the relation between Q123 and Q132?
They're inverse to each other.
Ah, okay.
Yes, yeah. It's
so
just
right? So it's x something times x.
Just if you just go to this relation, yeah.
Mm-hmm.
Just go here. Here is this. No. Here. You see, if you change the order of y and z, then they change, and it is just equal to q z y x minus first. It's just evident.
Okay.
It's from this formula.
Thanks.
Yeah, it's just notation, just a piece of notation.
Mm-hmm.
Okay, so now I think I'm going. There are different paths I can take now, but I prefer to speak about some geometric stuff again, not elementary geometry though. Actually, it turned out that expressions similar to this non-commutative cross ratio expressions appeared pretty long time ago in various papers without understanding of this, under some certain kind of additional assumptions. So I'll speak about one example of such appearance, of such occurrence, which I can refer to, which appeared in a paper by Mikhail Zelikin. Probably better not kappa of this sort, about this kappa. I'm speaking about so-called non-commutative. Sorry, I can hear some echo. So can you please turn off the microphone unless you're going to ask me a question? Echo can be very disturbing. Thank you very much. Okay, so it appeared in a paper by Mikhail Zelikin, but after under kind of a small inspection, short inspection, turned out that very similar expression appeared some 50 years ago in a paper in a book by Wu and Zun. Some Chinese, I think it was Wu and Zun, but I'm not sure about this. So I'm speaking about so-called operator cross ratio. Operator cross ratio.
Gosha, in Russian, he is known as Hualoken.
Sorry, Hualoken, yeah. Yes, sure, Hualoken. I just, I'm sorry if there is a Chinese person here, but sometimes it's really very hard to remember Chinese name. Yeah, Hualoken, thank you very much. Hualoken. I'm speaking, so suppose we have a Hilbert space Finite dimensional, infinite dimensional actually doesn't matter very much, which we can represent as a direct sum of two subspaces of the same dimension, V1 plus V2. For instance, you can assume that we work with finite dimensional to n-dimensional space, and we fix its decomposition into the direct sum of Kn, two copies of Kn. Definition. Polarization of H is any decomposition of H as a direct sum of P1 plus P2, where Pi is isomorphic to V1. Actually, we assume that V1 is isomorphic to V2, and we fix this isomorphism. In this case, this isomorphism is given by just by fixing the coordinates, just by fixing the basis. So we can actually assume that the basis is fixed, and that's all. Now, suppose we have such polarization H P1 plus P2, and let P4 and P3 be another polarization of this sort. Oh, sorry, P3 plus P4. Let us denote by Pi the map from H into okay, let's, I think it's better to be shorter. It's just a projection of H along Pi with respect given by this decomposition. So it's projection to the complement space. So we finally give the following definition. Take P1 and take projection P4, pi4. It will send you to pi3. Then you use pi2 and it will send you back to pi1. This is an operator from pi1 to pi1. And this operator is called the double, well, this is the notation from the paper by Zelikin. Pi1, pi2, pi3, and pi4. It's just this composition. If we fix the original polarization, say this one, right? Then you can represent every subspace pi I in terms of this polarization star twiddle as the graph of certain linear map pi I. You can write that pi I is equal to the set of vectors of the form f pi of f. F is in V1. In terms of PIs, we can now, in the separators PIs, we can now write down explicit formula for this this DV, this non-commutative operator cross ratio, P1, P2, P3, and P4 as the following product. We first take the difference P4 minus P3 and take inverse of this operator multiplied by, sorry, it's not P2P, I'm sorry. I looked in a different place. It should begin with P2 minus P1. Bless you. P2 minus P3 times P4 minus P3 minus first, and times P4 minus P1. So if you want, I can spend some time proving this, but it's not very hard to just think about what it means to be equal to a projection. And then it is straightforward to write down this formula very, very quickly. Now it goes as a very simple observation that if you take the elements 1, P1, 1, P2, that would be, say, X, Y, 1, P3, and this be Z, and 1, P4, that would be T. They all belong to the Cartesian product, Cartesian square of the algebra of endomorphisms of V1. Right, then you can write down this cross ratio, the comparator cross ratio of Sharygin as, well, up to the permutation of P1, P2, P3, and P4. It should be something like K, P3, P2, sorry, P2, sorry. Not this. Z, Y, T, X, something like this. So it turns out that this relation already appeared a very long time ago. And now this expression has a very nice geometric interpretation. So I hope that the generic case, arbitrary division ring F, you can also give a nice interpretation of the cross ratio. Namely, the claim is as follows. This dV of P1, P2, P3, and P4 plays the role of the coordinate change. Sorry, is something wrong with my microphone? No. Okay. There's the role of the coordinate change in the. I'm sorry, I can hear some very strange noise in my headphones. Am I the only one?
No, I hear something.
Oh. Okay, thank you.
Everybody hears this. I think that someone had just microphone non-switch.
Mm-hmm. Yeah, so I kindly ask you to turn off the microphone as long as you are not asking questions, because listening to this sounds is a little bit disturbing. Okay, so it's change of coordinates in the Grassmannian space of polarizations. Let's put it this way, H, V. Just to draw I try to draw the picture to explain this. You have two, so as you know, Grassmannian, the charts, the coordinate charts in Grassmannians are determined by the choice of representation of every space in some open set in Grassmannian as a graph. As long as you can represent some sets, some planes, some hyperplanes as graphs, you can identify this set of these hyperplanes with a set of all matrices. This actually gives you the coordinate chart in Grassmannian. So let us choose two graphs, sorry, two decompositions of our Grassmannian into, sorry, of our weak space into direct sum of subspaces, assuming that P1, P2, P3, and P4 are all transversal to each other. I can do it in two different ways. I can take P4 and P1, and then we can represent H as the direct sum of P4 and P1. Else I can take again P1 and P2 and represent H as the direct sum of P2 and P1. Now every hyperplane P3 in this, well, which lives in general position with all three other hyperplanes, I can represent it as a graph of a map from P1 to P4, or else as a graph of the map, some different map from P1 to P2. So eventually it turns out that the change of coordinates from this representation, from the first representation to this representation, is given by multiplication, by composition with this cross ratio. This cross ratio is a map from P1 to P1. So if you take composition of G with this, of F, sorry, I think just, yeah, or if you take composition of F with this cross ratio, you obtain G. As far as I can understand. So this is the definition. This is the geometric interpretation of operator cross ratio. I really hope that something like this can be done in general case, although I don't know how yet. Another important concept which is related to the cross ratio and which also appeared in the geometric studies of operator cross ratios and even in control theory is the notion of Schwartz derivation, Schwartz derivative. Let me recall you the definition of Schwartz derivative. Schwartz derivative. Let F be a map from projective line to projective line. We can assume this to be complex or real projective line, doesn't matter. Take any point T in projective line and take T1, T2, and T3 to be infinitesimal shifts of T. Namely, you can imagine that P1, suppose we work in projective or in real projective line, and it is just S1. And then you have this vector field d over dt on this line. And then we have T1 equal to T plus epsilon V. T2 is equal to t plus 2 epsilon v, and t3 equal to t plus 3 epsilon v. Then we can do the following trick. Take the cross ratio of the images of ft, that is to say of ft, ft1, ft2, and ft3, and find the infinitesimal part of this in terms of epsilon. It turns out that first you will obtain just the cross ratio of t, t1, t2, and t3, but then there will be epsilon square. Epsilon first degree of epsilon will vanish, but then there will be epsilon square times certain expression depending on f at point t plus something which will be of higher degree in epsilon. Probably here they sometimes also use 2 here just to, and also change the sign from plus to minus just to fix, to make it look like the classical one. S of f can be written down explicitly as the triple derivative of f divided by the first derivative minus 3/2 of f double prime divided by f prime square. This is very famous invariant. It is so-called Schwartz derivation. It has lots of properties. For instance, S of f is equal to 0 if f is projective. Projective transformation. It is almost evident that it should be equal to 0 if it is projective. It also verifies the so-called cosine correlation, namely if you have composition of G and F, and it should be equal to S of G times F plus S of F. In particular, it actually depends on the choice of coordinates. It is not tensor. And it turns out that one can actually find a noncommutative analog of this. Now, noncommutative analog is very straightforward. You consider, so let Z be a f-valued function. F is our division ring. And we consider the function f t, t1, t2, t2, t3 to be equal to the cross ratio of z of t, z of t1, z of t2, z of t3. I'll speak in scientifically. I embed f into a projective plane, a projective line of f as an affine subspace, but informally it is just this kind of thing, and so on. And now we can write down these as well, decompose it, expand it in terms of T1, T2, T3, and T4, assuming that T1 and all the other, all these T's are central in the algebra. And it turns out that what we have will look like the usual cross ratio of T1, T2, T3, and T4. Times 1 plus infinitesimal part T2 minus T, T3 minus T1, And now here comes noncommutative Schwartzian of f, of z rather than of f. Plus O of epsilon square, of silent square. Here, noncommutative Schwartzian of z is this expression, is z prime minus first z triple prime minus 3/2 z prime minus first the double prime square. As you see, here we have successfully resolved the problem of quantization. I have chosen the order of product of terms in this product in some canonical way, and because in general z prime need not commute with all the rest of the z double prime. So this is the noncommutative relation, and it turns out that it also has all the properties I mentioned. It is definitely also projective invariant. That is it just follows from the definition. As far as this second property is concerned, you see we cannot substitute z into z because z takes values in noncommutative division ring, while its argument is in real numbers. So we cannot do this, but as long as we choose any diffeomorphism of real numbers, f to be diffeomorphism of real numbers, this formula is preserved. So now here, this S of f is the classical Schwartz derivative in the classical sense. And this one is just this. It is remarkable that the first place where I found this, well, historically, the first paper in which similar formula appeared was a paper by Agrachev and Zelentsov, I don't remember the name, and then related to the study of so-called Zelenko, thanks. It's dedicated to the study of Jacobi curves. So it is very interesting that in that study, this expression had the meaning of a curvature of the curve. So I think the geometric consequences of this are well fascinated to study. Okay, I think one last thing I need to mention before I stop completely is the following observation, that actually one can obtain noncommutative Schwartz derivative from noncommutative differential equations in a manner very similar to the classical one. Namely, assume that our f is equipped with a derivation d partial d from f into f, which verifies the Leibniz rule, but is not commutative, usual Leibniz rule. That is to say, d of ab is equal to dA times b plus a db. Then we can, using prime to denote this derivation, we can consider the following system of differential equations, well, kind of differential equations in f. For instance, here f double prime 1 plus a f1 prime plus b equal to 0, f double prime 2 plus a f prime 2 plus b equal to 0. Actually, it is just the linear differential equation of degree 2, and we look for, so to say, the fundamental matrix of solutions of this differential equation. It is convenient to write it down in terms of a system. Then we can consider the following change of variables. Fi goes to Fi trivial equal to Fi times h for certain h. or H times Fi. H times Fi. And the following is the one of the results of our paper claim. Suppose H prime is equal to 1/2 H A. Also put phi equal to F1 minus first F2 theta equal to phi double prime phi prime minus first. Then under this change of variables, the first equation turns into the equation F twiddle 1 prime equal to minus F twiddle 1 divided by 2 theta. And the second A twiddle is equal to 0. B twiddle is given by the formula 1/2 F twiddle 1 theta prime minus 1/2 theta times F twiddle minus first 1. So this gives us the change of variables, and I make the observation that this...
I'm sorry, B should be multiplied by F1 and F2 in the system. Is it correct?
Sorry? Here,
B should, it's not homogeneous equation. B should be multiplied by F1 and F2, yeah?
I mean, here, I don't understand. You can make this correction.
I mean above, when you have a system, F1 double prime plus A F1 prime plus B multiplied by F1.
No, it's not homogeneous here.
Not homogeneous.
It's not homogeneous. At least as far as I can understand. I made these computations myself, so probably it should better be multiplied by something, but these computations, I made it myself. I checked them myself because it all began with observation by Vladimir Retach, and then I changed it. I checked it myself by hand, and this, I can, I can well, swear that this is correct, this formula is correct, unless I made a mistake in rewriting it right now. Yeah, so what the purpose of this was to make observation that theta prime minus 1/2 theta is actually equal to the Schwartz derivative of phi. So this is a kind of, I think in classical case, when you work in classical differential equations, this is called, well, Volodya, do you know how this is called in classical case? This is called Schwartz equation. I don't know. So it's actually the way Schwartz derivative appears in the solution of linear differential equations, and it does appear here as well, as you see, even though all the coefficients are noncommutative. So there should be something important there, although I don't know what. Yeah, I think that's not all what I can say, but I think it's better to stop here. It's already pretty much time, right? Yes.
Thank you very much.
Yeah, you're welcome. If you have some questions,
yeah.
I'll try to answer them as much as I can, as well as I can.
If not, I have some philosophical general question about what do you think, how it could be coherent with other way to quantize algebraic object, for example, the theory of quantum groups.
I don't understand. So can you repeat this?
You, in a sense, you construct in the first part of your talk, you construct some non-commutative analog of the theory of homogeneous spaces, Grassmannian. So.
Oh yeah, yes, one can. Yeah, this can be done somehow.
Quantum group situation. So it's a very special way to quantize something which acts.
Yes. Right.
Can I say something, Dima?
Surely.
You know, here is a very important ingredient is so-called Gelfand-Rietveld quasi-determinant.
Yes.
And after these quasi-determinants appeared, there was a attempts in the case when the non-commutative ring is not very non-commutative, by say Q-commutative, to compare the quantum determinants and quasi-determinants. And they are very well compatible. So
yes, but quasi-determinants are more than Q-determinants.
yeah, of course. But quasi-determinant is not a determinant; it is a ratio of determinants.
Yes, it is. Yes, ratio. In fact, there is a. Of course, one can try to use quasi-determinants to obtain the quantum homogeneous spaces, although
Yeah,
I don't think this has ever been done.
Blücher coordinates. It's just a manifestation of this non-commutative Blücher coordinates.
Sure, but well, you see. Well, as far as I'm concerned, I know several approaches to quantum homogeneous spaces, and I don't know which one should be preferable over other ones, because all of them have well, some advantages, some disadvantages. Depends. Yeah. It all depends on what you really want to do with these homogeneous spaces. In my opinion, probably it's just because of my well, original topological background. The most important thing is these cycle relations, co-cycle relations, which we used before, those cycle and 5-term relations of dial logarithms and so on. So that's what I think about now. And I think in this case, one can find suitable generalization of quantum homogeneous spaces as well. As far as you ask, well, what you ask about is another approach, which is based on quantum groups. Probably they also will yield you some nice definition of quantum homogeneous space, but I'm not sure they will be the same. See.
Thank you. I have another question, but it is mostly for Misha here. Does this approach have something common with quantum cluster algebras? Misha, do you think? Do you have some idea, Misha?
Can I? Well, this quasi-determinants, right? Yes. These Schur complements, they appear in this non-commutative cluster algebras everywhere, but it should have, but I don't think it's known.
We, you know, there is a very, very interesting question, which probably Volodya Retach and Bernstein knows the answer. You know, we know that the usual cross ratio can be considered like a coordinate on the local system of sphere minus 4 points on the moduli space of connections, if you want, on the sphere minus 4 points. And now the question, if we have a non-commutative local system in sense of Kontsevich, can we use this non-commutative cross ratio to coordinatize this simplest analog of it?
Yeah, I think the answer to that is yes, right? It's what
yes.
Bernstein and Retach did.
Well, but they did it in maximally non-geometric way. Maybe. No?
But kind of, I think the answer, the question, is it possible to generalize beyond this geometric situation, like this description of non-commutative local system is not known?
Yeah.
Well, so we are working on it, but there is a related question, and this is about this Ptolemy identity, which is also sort of in this area with the game with the non-commutative Ptolemy identity is done.
Mhm.
And
Okay.
so we wrote a paper on this.
That's more than I can say. I mean that right now, at the moment, I'm a little bit tired. So I just enjoy listening to the discussion.
So I'm a little bit tired as well, because in 1 hour I have another long-term group de travail online. So I want to say bye-bye to everybody. Thanks a lot, Gosha, and thanks a lot, everybody.
Yes.
And I hope tomorrow.
Yes, I really hope. Just let me know what time you prefer to continue.
Volodya is quite.
Yeah, so I think I shall schedule it for, say.
Yeah, because we have tomorrow there is a Poisson seminar and there is a cluster seminar. Maybe after all.
So when will the second one stop?
Poisson seminar is from 5 to 6 European time.
Yeah, so after 6 probably.
Okay.
European
so
time.
In 7 Moscow time. From 7.
It's for Volodya. I don't know if he teaches or not.
Yeah, I'm teaching after 3 o'clock my time, which is actually like
I think it's 10 p.m. Moscow time.
10 p.m. Yes, 10 p.m.
And
Moscow.
9 p.m. European time. Oh.
No. So you are free at
Before that.
Before.
Yes.
Okay.
Okay. Well, okay. So, Volodya, if I can take a look at this group de travail, I mean, I would probably enjoy. Can you please send me a reference if it is possible?
I should say Goloshev to do it, because he is the organizer.
Okay. Thank you.
Okay, I would like to thank everybody who attend this seminar and our meeting, and I hope we will continue. We will probably discuss in the community what the next talk we want to have, and we will, I think will be helpful if you send kind of feedback how it works, and do we really enjoy this kind of seminars. And I think we should continue, because that is a way how the community can stay together in this difficult time, and we will all benefit from this seminar. At least I enjoy this seminar, and thank you very much to the speaker and to everyone.
Yeah, thank you for inviting me.
Sasha, for organization. And I have a question for British colleagues. Do you know the next integrable system virtual seminar data?
Well, I think it hasn't been announced to us either.
Mm-hmm.
Probably, you know, most of the universities have started kind of Easter break this week.
Ah, I see.
I think Ian Strawn and Peter Clarkson are preparing the schedule for the next one.
Okay. Just to make some correlations, because too many interesting things, we should correlate things.
Yeah.
Okay. Should coordinate.
Yes.
So bye-bye.
Bye-bye.
Thank you very much.
Thank you.
Goodbye.
Bye.